Okay, anyone who doesn't want to be recorded, you can keep your video off. So it is a great pleasure and a tremendous honor to introduce Professor Saul Kripke, who's our speaker today at the higher seminar in theoretical philosophy.
Is there a lower seminar?
No, maybe there was. Peter, maybe there was at some point. So I'm very delighted to introduce Saul to present here, but I also find it somewhat a daunting task, because if there's anyone in philosophy who needs no introduction, it's Saul Kripke. I think every student who's taken a course so much as for a few minutes will have some familiarity with Kripke's work. And if I tried to summarize everything, the myriad ways in which Kripke has influenced the discipline of philosophy, I think we would take up all of our time. So what I will just say by way of introduction is that Kripke has, his work has been extremely important to me personally in my career. I find it incredibly inspiring, even on the 150th reading. And I'm very much looking forward to hearing him speak today to us. It answers to the question, is mathematics the handmaiden of physics? Welcome, Saul.
So I'm going to say something. Usually Saul has trouble making a decision about what topic to pick for a talk, and drugs and so on. But out of the blue, he came up with this, and then later he said, "I must have been in some mood." Is mathematics a handmaiden of physics? I don't know why you decided so quickly that you wanted to do this. Probably you had been reading something that upset you or something.
Maybe. Okay.
Well, thank you, Anandi.
Thank you, Anandi. I think there are sort of popular views that mathematics and physics are one subject, that they go together, and unfortunately, some variant of this view has seeped into philosophy. It should be stated really that there isn't even any one subject to be called mathematics. I mean, there's a common core, but then it's so specialized that one mathematician doesn't know what another one in another area is talking about, right? And can't understand. Well.
Okay, so the title is?
Okay, the title is, well, I just said it, is math. What?
Yeah, okay.
Yeah, and this is based on various philosophical, this is about various philosophical arguments that think the only justification of mathematics.
And you're going to answer yes to that question, right?
Yeah, actually, yeah. God, that's a silly thing. Yeah, of course I'm going to answer. Actually, obviously, if someone raises a question like that, the answer is no. God, Romina reminds me of a sort of joke title for a talk. Was Berkeley really a materialist? And then the answer is no, of course not. Whoever thought so, right? Yeah. Okay. Now, in fact, here is the idea. Various philosophers, when faced with skepticism about the truth of mathematics, supposedly because it commits one to abstract objects, which are supposed to be dubious entities, have argued that mathematics is justified because it is used in physics. This is called the indispensability argument. Noted advocates for this argument are Quine and Putnam, though I have found it somewhat hard. I've got some references.
Especially with wine, I would say.
Yeah,
I prefer find clear statement.
A clear statement of this, though Quine is actually supposed to be the father of this kind of view. I think he really would have hoped to be a nominalist and not favor abstract entities, except because of their use in science. Noted that, yes, okay. Yeah, objectors to the argument have stated, well, I'm going to go into this, that weaker systems than conventional set theory suffice for existing physics, Pfefferman being a prominent example. I'm going to mention Pfefferman. Or that mathematics does not have to be true to justify its use in physics. Hartree, Field, and so Field actually rejects any idea that mathematics is true.
Yeah, I mean, they object to the indispensability argument, but they agree with this idea that the justification for math is in physics, right?
Yes.
Yeah.
And since
which is the point that you're going to dispute, right?
Yeah. Yeah. Okay, so yeah. And okay, I might say that as against this entire debate, I can only agree with David Lewis, who in his book, Parts of Classes, states, renouncing classes means rejecting mathematics. That will not do. Mathematics is an established going concern. Philosophy is as shaky as can be. To reject mathematics for philosophical reasons would be absurd. We shouldn't expect mathematics to go away to make our life easier. Even if we reject mathematics gently, explaining how it can be a most useful fiction, good without being true, we still reject it, and that's still absurd. Even if we hold on to some mutilated fragments of mathematics that can be reconstructed without classes, if we reject the bulk of mathematics, that's still absurd. By the way, I have some funny side comment. Hilary Putnam is actually an exception to this. Mathematicians, when they talked about set theory and sets, right? They use the term sets. Philosophers, such as Quine and Lewis, seem to prefer classes, which in ordinary set theory is only used when one's talking about so-called proper classes. Now, David is right. That's not our argument, I know. Rather, I moved to laughter at the thought of how presumptuous it would be to reject mathematics for philosophical reasons. How would you like the job of telling the mathematicians that they must change their ways and abjure countless errors now that philosophy has discovered that there are no classes? Can you tell them with a straight face to follow philosophical argument wherever it may lead? If they challenge your credentials, will you boast the philosopher's other great discoveries? That motion is impossible. That a being than which no greater can be conceived cannot be conceived not to exist. That it is unthinkable that anything exists outside the mind, that time is unreal, that no theory has ever been made at all probable by the evidence, but on the other hand, that an empirically ideal theory cannot possibly be false. These are both views. That is a wide open scientific question, whether anyone has ever believed anything. And there's a book he's referring to called The Case Against Belief, trying to get you to believe that there's no such thing as belief, right? And so on ad nauseum. Not me. I remember saying to David, I really like this, and that I really feel very emotional about the reaction he's condemning. He, of course, doesn't mention.
Oh, yeah, I was going to say, did you ask him why he doesn't include the counterparts there?
Yeah, well, he doesn't include the discovery of philosophy that there are all these disjoint portions of space-time in which all possibilities hold, right? Okay, now, this is not to say that such work as Pfefferman describes might be interesting as an expression of how much one can get from a weaker philosophical position than is presupposed in current mathematics. And I might say, for example, I've been interested sometimes in intuitionistic mathematics. I don't necessarily accept the philosophy, the views on which intuitionism was based, but just thought it was an interesting thing to work on. Michael Dummett mentions that there are people like that, such as Kreisel, that's what he cites, right? But yes. Okay, now, however, I personally find the idea that mathematics has to be justified by its use in physics quite repellent. Perhaps it's simply that I didn't like physics as much as mathematics, so I learned some, right? Most of the mathematics that I studied in college had no purported connection with physics, but was simply studied by mathematicians because of its elegance and naturalness. Such a result is Andrew Wiles's proof of Fermat's last theorem and the appropriate results from algebraic geometry would appear to have no use in physics, but they are studied by mathematicians because of their intrinsic beauty and because of a gripping desire to solve a problem. Now, one mathematician I talked to said it's a little strange that Fermat's last theorem became such a classical problem as opposed to various other number theoretic problems. And I thought it was because Fermat said he has a wonderful proof of this, right?
Right.
But he cannot write it down. And lots of work was done over centuries to get it. And it was amazing that it finally was proved. There are many things going up to Andrew Wiles. I mean, he can't really be said to have done it all by himself, right? I once discussed this when Quine was giving a talk and said that I offends my mathematical soul to think that usability in physics is all the merit that mathematics can have. Quine, and that I thought that there are all these other things in mathematics. Now, Quine is not as strong about this ever in print as I recall. I remember Charles Parsons saying Quine's real attitude came up much more clearly in this discussion, which was just at a conference, right? Quine compared this attitude, that is my attitude, right, to a fictional chess player who gets so absorbed in the game that it drives him mad. So this refers to a novel by Vladimir Nabokov called The Defense. This is a pretty early work of his.
What did he say when you said that that the offense, your mathematical soul? What did he reply to you? I mean, it wasn't the question. No, maybe he didn't reply anything, but.
Well, I don't know. This is more or less his reply.
Oh, he replied. Okay. So he replied with that. No, that wasn't part of the talk. Okay, I see.
What?
He replied quoting that.
Yeah.
Mentioning that. I see.
Yeah, he mentioned. So I guess he had read that book.
Yeah.
It's a very early work by Nabokov. Though to my surprise, I found that it's been made into a film much more recently. I mean, I don't know anyone has seen it or anyone's read the book. I sort of have read the book.
Yeah, one thing that I heard you say once is that people think that analytic philosophy is mathematical philosophy or something, but actually a lot of the attitude is not very mathematical, like Quine, Putnam, and so on. They were quoting,
Yeah.
What they mean is something else, obviously, that there are a lot of symbols.
Yeah, no, I mean, look, someone, I don't know whether other people are facing this. I once talked to someone who actually had a degree in philosophy, but not in analytic philosophy. And I thought I could give this man a copy of Naming Necessity. He said, well, I don't know if I'll be able to read it since it will be full of equations. And this represented two sort of misconceptions. First, that contemporary analytic philosophy is all mathematical, and sense that mathematics consists primarily in equations, neither of which are true. I wrote one paper that was indeed full of equations, but it didn't purport to be philosophy at all. It was simply a mathematical paper. But most mathematics doesn't involve equations. More, I think physics has more. Okay, well, here we go. Let me go back. Some of the authors I'm speaking about were worried that mathematics postulates entities that, being abstract, are ontologically dubious. Quine, who was tempted by nominalism, that is the rejection of such entities as numbers, classes, and so on, nevertheless became convinced that we must accept them as entities because they are used in physics. Yeah, he wrote a paper defending nominalism with Goodman, and now he said that he never really believed this or something. I don't think that is probably really true. And Goodman did believe it. They have footnotes as to why set theory or classes are not acceptable, like the existence of alternative systems of set theory, right, to avoid the contradictions of Russell's paradox. Makes it look as if we obviously are playing in a land of make-believe, right? Was a footnote in this paper by Quine and Goodman. Though Quine wrote somewhat tolerantly of such subjects as abstract algebra, his attitude seems to be that failing application to science, and particularly to physics, these are excrescences that we must accept to round out our set theory. And I have a quote. Yeah. Yeah. In a higher sense, well, this is it. Even abstract algebra and the abstract geometrical studies may be said to be fully interpretive studies at all. After all, they are chapters of set theory. A group for existence, he likes to do things the way mathematicians don't do it. A group is usually defined as a set together with an operation on it. The group operation. He was proud of saying that referring to the set is superfluous because it will just be definable as the domain of the operation, right? And only the operation needs to be identified with the group, right? So it's simply a function of a certain sort. It is any associative two-phase function having a unique identity element, and for each element, an inverse. But a two-place function is a set of triples, and that's group theory is the part of set theory that explores the properties common to functions that meet these conditions. Other abstract algebras can be identified in a similar spirit, right? Okay. Now, I will say that in addition to physics, he mentions, of course, elementary arithmetic, which really is not so much justified by use in physics, but in our daily life and counting and so on. And that is right? So in the interchange with me that I mentioned, but which of course never saw print, you thought it did?
No, I thought that maybe the analogy with between the mathematician and the character from Nabokov's novel was something that was already, that he already said in his talk, you say.
No, it's something he said in reply to me, I think. Yeah.
So what's the idea? You go mad if you do mathematics for its own sake? I don't know.
Yeah. The sort of highlight, though not the end of the book, is a chess game with a formidable opponent, right? Which is never finished because the title player, I think his name, well, whatever his name is, sort of collapses and the game is never finished. People wonder who would have won, right? Things like that. All right. Okay, in the interchange with me that I mentioned, but which of course never saw print, his attitude came out fairly clearly. Now, Hilary Putnam was a philosopher who was perpetually changing his mind. So it is somewhat hard to speak of Putnam's view on any subject. I remember talking to Hilary about this, did I say? Yeah.
Yeah, you tell me what he said.
No, I said, so you adopt different views at different times. And then he finished my sentence for me. And I feel very sure that I'm right each time. Right? And I said, well, so what about that? And he said, well, it makes you feel better to defend a view by really thinking that now you've got it right. Okay. In some talk of his, he tried to mention things that he had not changed his mind about all throughout his work. So here is Putnam's view in 1971, though some things here are strange because a different view that I'm going to cite, it was published in a book later, but the paper seems to have been published earlier than this thing in 1971. So I don't know what the relation between the two views is, and there would be no trace of the second view, which was actually published earlier, and unless the book was written earlier, right? Then okay, here, so Putnam says, so far I have been developing an argument for realism along roughly the following lines. Quantification of over mathematical entities is indispensable for science, both formal and physical. Therefore, we should accept such quantification. But this commits us to accepting the existence of the mathematical entities in question. This type of argument stems, of course, by the way, I don't know what he means by formal and physical. Physical means physics, I suppose. What is formal science? This type of argument stems, of course, from Quine, who has for years stressed both the indispensability of quantification over mathematical entities and the intellectual dishonesty of denying the existence of what one daily presupposes, but indispensably raise a number of questions, some of which I would like briefly to discuss here. So, well, I don't go on with the full discussion, but Putnam goes on to defend the meaningfulness of such locutions as numbers exist, sex exists, sets exist, and so on. He argues that anyone who accepts the meaningfulness of there exists a prime number greater than 100 must a fortiori accept the meaningfulness of there exists a number, comma, and so on, because if there exists a prime number greater than 100, then it follows that there exists a number, right? Yeah. Okay, right. It is interesting to note that in the previous chapter of the same book, Putnam speculates, given predicative set theory, one can easily define the rational numbers, sorry. Thus, it appears possible, though complicated and awkward, to do physics using just predicative set theory. He seems to think that predicative set theory does not allow the reals, right? And one could somehow do physics allowing only rational numbers. Actually, Putnam does not here seem to be aware of some of the strengths of predicative mathematics as it came to be defined by Weil, Kreisel, and Pfefferman, and others. It would be less awkward if one could use the full strength of the developed theory. Well, I'm going to mention Pfefferman eventually. One should also mention Putnam's interpretation in his paper, Mathematics Without Foundations, which actually gives something of foundational proposal. Well, I mean, he thinks rightly. I think the mathematics doesn't have a foundations crisis the way some people have thought, right? But I mean, and well, during a certain period, this was accepted, like Hilbert thought there was such a problem, and so on. And Brown, okay, and Brouwer tried to fix it by reinterpreting mathematics and so on, right? Okay, but his proposal is, namely, that mathematics can be interpreted in terms of modal logic, as stating what follows from various assumptions. His example is the negation of Fermat's last theorem, and pages 47 to 48 of this book, right? Philosophical Mathematics, Matter and Method, is a development of this. So look, somehow we haven't been able to get this onto the PowerPoint, right? So I'll have to just say it.
Yeah.
Okay, it's box that is necessary if AX, ST, well, AX, ST are some rather weak axioms, then not Fermat, ST. Well, ST is can be some sort of statement of some very weak system, because the reason Putnam chooses to deal with the negation of Fermat's last theorem is that if there is a counterexample, it is provable from relatively weak axioms that there is one. Of course, we now know that there is no such counterexample, right? However, I presume that the modal picture is supposed to apply even if, in fact, as in fact has now been proved, Fermat's last theorem is true. Okay, and Putnam says, here, in fact, if one fastens on the first picture, parentheses, the object picture, then mathematics has no special objects of its own. But simply tells us what follows from what. If Platonism, well, I thought the first picture is that it accepts the existence of mathematical entities. Yeah, the so-called object picture.
In the philosophy of mathematics of present.
Yeah. If one passes on the first picture, the object picture of mathematics is only extensional. I think something is really, yeah, something is bad on the PowerPoint. Something has been deleted.
Platonism has appeared to be the issue.
Yeah, in short, if one fashions on the first picture, the object picture, the mathematics is only extensional, but presupposes a vast totality of eternal objects, right? I don't know why this has gotten bad on the PowerPoint where we skipped.
Well, you know, if you decide to start doing the PowerPoint, we might have been able to check it.
Yeah. Well, we should have. Yeah, well, it fastens on, if one fastens on the second picture, the modal picture, then mathematics has no special objects of its own, but simply tells us what follows from what. Okay, this is somehow it's condensed so as to not make sense, right?
Yeah.
If Platonism has appeared to be the issue in philosophy of mathematics of recent years, I suggest that it is because we have been too much in the grip of the first picture. Okay, and he actually says that the modal idea could actually be used even for higher set theory and so on, and rightly thinks, in my opinion anyway, that any particular model of set theory could be extended. Well, because it will have to be a set, and therefore it won't contain all the sets. I myself think that the sets have to be a potential totality and not a closed totality. And that is my view. Sorry that this has been garbled. I didn't really know.
Well, it's instead of I in.
What?
Instead of I in. But you want to include more than that, I guess.
Yes, I wanted to include.
I see. Okay.
Yeah. Okay, so as I said, one would have to develop modal precursors as one example, but I myself am sympathetic to the basic idea of this suggestion. Putnam does talk about how to do set theory in this modal matter later in the paper. Well, I've just said this. He talks about rank theory. In agreement with my own intuition about this, states that any particular model has to be thought of as extendable. Once again, he mentions the possibility of a predicate of set theory up to some low transfinite type. Even in this instance, one can see the talk of Putnam's view is not so clearly defined. In philosophy of language, he seems to emphasize the one picture in which the issue of whether numbers exist, sex exists, and so on is the issue. But in the earlier paper, see, this paper is published in a book later, but it seems to have been published in a journal earlier. I'm a little puzzled that maybe the book, Philosophy of Logic, was written earlier than its publication date.
Could be.
Yeah. In the earlier paper, it suggests a different and complementary modal picture, which does not appear to be mentioned in the Philosophy of Logic book, though I haven't read the whole thing. In both papers, however, he is concerned to get something adequate for science, in particular for physics. Well, so there are many other views of Putnam, even in short time periods, and considerable changes of position over long time period. Solomon Pfefferman wrote an elaborate consideration of the indispensability in his arguments, while a little goes a long way, logical foundations of scientifically applicable mathematics. Pfefferman believed that, quote, on the face of it, scientific realism is at odds with the strong form of Platonic realism required to justify set theory through its assumption of the independent existence of abstract entities, such as sets of sets of sets of sets of unbounded infinite cardinality. In spite of my rather passionate agreement with David Lewis about philosophy and mathematics, one might still be impressed, I think I said this, will be impressed with some of the technical work that has been done and how much mathematics can be done on the basis of various philosophical positions. In particular, this applies to the kind of predicativism advocated by Pfefferman himself and various others following Weil. Pfefferman, along with others, says, see, in considering what mathematics is actually used in science, it suffices to restrict attention to physics, since among all the sciences, that subject makes the heaviest use of mathematics. And there is hardly any branch of mathematics that has some scientific application which is not applied here. It would be foolish to claim detailed knowledge of the vast body of mathematics that has been employed in mathematical physics. However, then he goes on to say that one should cover 19th century mathematical analysis, at least of piecewise continuous functions on various bases, and go on to beg measurability in early 20th century functional analysis. Yeah, I know, I said functional mathematics and some typo. Once again, this project makes mathematics the handmaiden of physics. Okay, a typo. I myself would remark that the Brouwer fixed point theorem, not theory, is very important for some,
Yes, you're right.
what?
You're right.
For some of economics, general equilibrium theory, but its use in physics is minimal. I myself thought maybe it isn't used. David Lewis, we call him to follow, mentioned something in physics that uses it, but I'm not sure. But it's not really important. It's important for physics as it is.
Here.
Yeah. Given this, that is the overwhelming importance of physics.
Okay.
Pfefferman sketches a system of predicate analysis, finite type, which he observed the provably conservative over first order piano arithmetic. He also discusses other ideas in the reverse mathematics program of Friedman and Simpson. That's a different program. I am not familiar enough with Pfefferman's system of finite type to evaluate it. I do have some views of his development of Weil's original system, but it is very digressive to discuss this here, since eventually I will have a very different criticism of the indispensability arguments. And I do have some views of the reverse mathematics program. Once again, it would be digressive to go into them. Pfefferman concludes that the indispensability arguments, as far as I'm concerned, they are completely vitiated. Right. By this, he seems to mean they are vitiated as arguments for conventional set theory. Pfefferman does say some doubts whether his predicative system will account for current physics. For example, maybe current physics makes use of non-measurable sets or non-separable spaces, which cannot be proved to exist in his system. Penelope Maddy, whose evaluation of the independential arguments begins Pfefferman's discussion, makes two objections. One is that fundamental mathematical science is idealized, that is literally false. For example, the analysis of water waves by assuming the water to be infinitely deep, or the treatment of matter as continuous in fluid dynamics. I don't myself see this has much to do with the utility of mathematics in physics, but it does show that these idealized views are not only used, but are really important, as I have heard Putnam argue.
She says this in the paper, Indispensability in Practice, it's in the Journal of Philosophy from 1992.
Yeah, thanks,
Because
yes.
there are other people that keep defending very different, more sophisticated versions of these arguments.
Yeah. Actually, one just should use these idealized things. For example, to show that a square peg cannot go into a round hole, a smaller area, one does not try to reduce it to atomic physics, that is to quantum mechanics, but simply ought to use the idealized formulation. In fact, it's obvious, right, that can't be the case, but but one has to use the idea of really uniform continuous matter to justify this simple statement straightforwardly. Maddy's second objection is the scientific indispensability cannot account for mathematics as it's actually done. Here, Pfefferman states that really much weaker systems than Zermelo set theory, even subsystems of second order arithmetic, this is mistyped, suffice for the bulk of mathematical practice.
I'm pretty sure you said that.
What?
I'm pretty sure you said that. Okay.
Wow.
Yeah.
Yeah.
You want to say something else?
No. However, I do think that Pfefferman's position on applicability of physics, aside from the objections that will be the main point of this talk, pretty clearly cannot be right. In his predicative systems, maybe a great deal can be done. But does one really imagine that any working physicist would object to a mathematical argument to be used in physics, right? On the grounds that it uses an impredicative definition, as is commonly done in ordinary mathematics, which has no objection to this. It seems to me that the answer to this is obviously negative. Also, the statement about the bulk of mathematics is obviously a bit head. For example, Borel, misspelled B-R-E-L, determinacy, a striking result due to Tony Martin, D.A. Martin, depends on the axiom of replacement, at least applied to countable sets. Now, I should also mention Hartley Field's book, Science Without Numbers. I would have various technical criticisms of this book if I were really dealing with its program and results. In his preface, Field states that the real question is, what sort of account is possible of how mathematics is applied to the real physical world? He says that his view is that this question is the really fundamental one. But this is, again, the indispensability issue, right? He mentions other questions in the philosophy of mathematics, but he thinks the important one is, which he calls question D, is the really important one, and states that it has led to a surprising result. It is not necessary to assume that the mathematics that is applied is true. It is necessary to assume little more than that mathematics is consistent, end of quote, which is not on the PowerPoint. This was done in a hurry. Okay.
I mean, I told Hartley once that that you thought they should have been called physics without numbers.
Yeah.
And he said that that was a fair criticism.
Yeah. Okay. Although I'm not a fan of Field's books as a technical contribution, what I do wish to stress here is how different is his view from that of David Lewis, as quoted above. Field does not base his idea on any restriction to weaker systems, as in Pfefferman's paper, but simply on certain technical claims. We need not go into this here, but the main thing as a philosophical needs to be given for whether mathematics is true, and the indispensability argument is, he thinks, refuted, right, by the weaker assumption about mathematics could be made. Okay. Now this is the real conclusion of this paper, right, which is very brief. There's some trouble.
Yeah, go.
Let me finally state what I think of this type of use of physics as a justification for mathematics. The point is that physicists do not seem to care that much about whether the mathematics they use is valid. I know what I mean by is valid, right? In a general way. When I read an important physics textbook by, oh gosh, I thought I dictated to you how to spell the name.
You did. Well, the first one is wrong, right?
No, the second one is just wrong.
I actually picked that up from Google, so.
Wait a minute. No.
You weren't sure about how to spell it, so.
I think it's Landau and Lifshitz.
Okay.
And it's not Lifshitz.
Okay.
I think Landau is sort of the senior and most famous author, but I think it's mostly actually written by Lifshitz. Where did you? There's no.
No.
Okay. Okay, they explicitly disclaim mathematical rigor. Moreover,
Yeah, I see it. It's Lifschitzc.
yeah,
Yeah. Okay.
yeah, Lifshitz, not whatever you've written there. Gosh, Romina buried a lot of the PowerPoint, which I take the blame now. I should probably really take the blame.
Well, it was 3 a.m.
Yes.
So.
Moreover, as a compliment should be spelled with an E, right? Okay. To victories.
If you go on, so go.
Well, both uses of compliment should be spelled to an E. They're not praising anything. But
compliment, yes.
Yes. As a compliment to Wigner's famous paper, The Unreasonable Effectiveness of Mathematics in Natural Science. That is how much mathematics really gets used in physics, which is true, right? Okay, right. There is a complementary, not the paper complimenting.
I thought it was weird.
What?
I thought it was weird, but I wasn't going to question anything at that point. Go on.
A complementary paper in the opposite direction.
Okay, read the title.
Supplementary paper. Right, anyway. The Pernicious Influence of Mathematics on Science by J. Schwartz. We have it here.
Somewhere.
Well, it's not on the table, I don't think. Unfortunately.
Okay. I can go pick it up if you need it, but let's go on.
Okay. Okay, so I'm not exactly sure even who J. Schwartz is. He discusses a number of things, right? One example that Schwartz gives is the, so you get how the pernicious influence of mathematics on science,
Right.
the exact opposite of what Wigner, right, seems to be saying, right? One example that Schwartz gives is the Dirac delta function. I myself remember in reading in a mathematics textbook a statement of what a Dirac delta function is, and an exercise being given show that no such function exists, right? Okay, right. Schwartz writes that the sorry history of the delta function should teach us the pitfalls of rigor. I do not entirely agree with what Schwartz says about the history of the delta function, right? He states, well, he also mentions its use in the 19th century, actually, right? But mostly attributed to Dirac. It was used constantly and systematically by physics since the 1920s. This function remained for mathematicians a monstrosity and an amusing example of physicists' naivete. Now, I don't know if that was the actual reaction of the mathematicians, though they did think that there was no such function. Eventually, Laurent Schwartz formulated the theory of distributions, which allowed one to consider the delta function not as a function, but as some sort of generalized function. Now, Schwartz presents it as if it turned out that it wasn't a function, but a generalized function, right? But it was the mathematicians who were worried about this enough to figure out a theory that would give some meaning to the delta function. It might be a proper function in non-standard analysis, I don't know whether that works for the uses of the delta function. Right. Of course that didn't, but yeah, so I just said this. Schwartz really misrepresents the mathematician's reaction, since they proposed an elaborate theory to justify the use of the delta function. Another example is renormalization. This is some sort of process where I don't really know the details that allows one to change a definite integral that gives an infinite value into a finite one. I hope I have this right. I don't really know that much about it, right? Amazingly just because of his introducing this non-function, right? Dirac, though he himself thought it was somehow some sort of limit, right? Maybe, right? Dirac himself did not like this device and thought that if one gets an infinity, it has to be respected. I am pretty sure that other examples can be found, and that in some cases, or I think many cases, a mathematical justification has not been found. For instance, in the case of the delta function, it was the mathematicians who tried to figure out a justification. The physicists simply accepted as it is, immediately thought of it justified as a limit. That Dirac himself made such a remark. I don't know what has been done for renormalization, but I am pretty sure, at least I've been told this, that the physicists were uninterested in any justification. As I said, my impression is that there are many other examples. Some parts of physics may be his two words, right? Mathematical rigorous. I think this is true of general relativity, though I'm not an expert on this, but this is my impression. But even in this case, it is incompatible with quantum mechanics, and the search for reconciliation has led to string theory. Here, the physicists haven't just simply laid back and said, oh, we accept both, right? They realize that they can't both be true. The morals here are these. First, if one accepts the indispensability arguments, one must justify a certain amount of false mathematics as indispensable, right? Right. And this somehow is not mentioned by people who give these arguments, right? This is not a very comfortable situation. Somehow the physicists have a certain amount of intuition as to what kinds of mathematical errors should be admitted into their theories. But this seems to me that false mathematics seems to mean that false mathematics might be justified by the indispensability arguments. I do not think that the cases I've given are isolated and exceptional ones. As I said, the physicists seem to agree when erroneous mathematics should be accepted in their theories and when it should not be also, right? Second, not only does this make the indispensability arguments problematic, there may be consequences for the philosophy of science generally. For if some physical theories are confirmed by predictions using erroneous mathematics, what does it mean for a physical theory being confirmed by its predictions, which are actually derived erroneously, right? So why are they considered the predictions of the theory? The physicists tell us that that's what they are, right? And some things come out very precisely right? Even with this sort of false mathematics. These last remarks, which are admittedly not informed by a great deal of knowledge of physics are the main moral of this talk. I mean, the main moral comes really very briefly at the end.
Okay, you're through.
Yeah.
Anani, should we take 5 minutes so he can go to the bathroom?
Yes, yes. Please take a 5-minute break and then we'll come back for questions.
Question. Good.
Okay.